Okay, awesome. So chapter 5, we kind of continue with probability here. And this is chapter 5 is all on discrete probability distributions. And specifically, section 5.1 is going to introduce what a probability distribution is. We have not talked about that yet. We just finished covering all of probability in itself. And now we're going to kind of apply some of the stuff that we've learned and learn some new things. So this section is going to be on probability distributions. And we're going to recall some definitions that we learned a little while ago. Not too long ago, though, since this is only, what, week 3? Okay, so the first definition is a variable. So recall that a variable is a characteristic or attribute that can assume different values. So various letters of the alphabet, X, Y, and Z, are commonly used to represent variables. We also talked about this thing very, very, very briefly. I think I literally defined it and said we would discuss it more later. And this is a random variable. So a random variable is a variable whose values are determined by chance. I think we talked about that like week 1, so that probably didn't make much sense, but it's going to make more sense because we've learned probability. Lastly, discrete variables are countable and don't include decimals or fractions. So this example that we have below here is going to just give you an example of maybe like a random variable and a discrete variable so that you can like visualize what one of these would look like. So an example would be rolling a die and letting X represent the outcome. So X would be equal to the numbers 1 through 6. So we talked about rolling a die in the sample space, how you can get numbers 1 through 6. And the reason why this is a random variable is because it's like outcome and its value that it takes on is determined by chance. So when you roll a die, whatever you end up getting, 1, 2, 3, 4, 5, 6, that's completely determined by chance. You don't really have control over what you roll, obviously, unless you like rig it and one side of the die is like heavier, but it's random. And then it's discrete because the amount of possibilities here that we have, first of all, there's only 6 possibilities that you could get, and there's no decimals or fractions. So a discrete variable is one where there's only a set number of possible outcomes. So rolling a die, there's only 6 possible outcomes, none of them are decimals or fractions, and whatever value this variable takes on is determined by chance. Okay. So now that we talked about that example, let's define what a discrete probability distribution is. So a discrete probability distribution, this consists of the values of a random, this consists of the values a random variable can assume and the corresponding probabilities of the values. The probabilities are determined theoretically or by observation. Okay, so this example that I'm going to do is probably going to just seem like, haven't we already done this before? And yes, we have kind of already done this concept before where we've talked about, hey, what are the outcomes of rolling a die? And what are the probabilities of each of those outcomes? So this is probably going to seem a little repetitive, but the way that we write it and that we're about to do in this example is what's called a probability distribution. So the distribution gives you all the possible values it can assume, and then its probabilities. So to do this example, like I said, it's probably going to seem like we've already done this. So the possible outcomes from rolling a die are 1 through 6. So my outcome or my like X right here is going to be 1, 2, 3, 4, 5, and 6. And then in the column next to it, we're going to put the probabilities for rolling each of those possible numbers. So like it said, the probabilities are determined theoretically or by observation. We're just going to use the fact that we know that the probability of rolling each of these numbers is 1 over 6. That's what we call theoretical probability. So, the probability of rolling a 1 is 1 over 6. So I'm just going to fill that in. Probability of rolling a 2 is 1 over 6. And the same for all of them. They all have equally likely chance of being rolled. So yeah, this is pretty familiar. we have done basically this example before. We just haven't written it in what's called a probability distribution. So we talked about, hey, what's the chance of rolling a 3? Oh, 1/6. But a probability distribution gives you every outcome along with its probability. Where in this column, P of X, as we talked about, is the probability of X. Okay, any questions on the probability distribution? Okay, let's do another example. So this next one says to construct a probability distribution for the sample space for tossing 2 coins with X as the number of heads. So again, another example that we've done before, but in this case, our X variable, so our random variable, is going to be the number of heads that we get when we toss 2 coins. So keyword for the sample space. So we need to go ahead and remind ourselves what the sample space is when we toss 2 coins. So if you remember when we learned this at the beginning, we used a tree diagram to identify what our sample space is. So I'll just recreate that off to the side. So I'm going to use a tree diagram, and on my first toss, I can either get a heads or tails. And then on my second toss, if I got a head, I can still get a head or tail. And same here, if I got a tails on my first toss, on my second toss, I can still get a head or tails. So this gives me that my sample space is heads, 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 tails, tails, heads, or tails, tails. Okay, so that's the sample space for tossing 2 coins. Those are all the possibilities that you could have occur. Obviously, we're kind of like ignoring if something lands on its side. We're just assuming a coin isn't going to land perfectly on the side. So now let's go ahead and make this probability distribution. So X is our number of heads. So we have to think, what are all the possible values that X could take on? So what are the possible numbers of heads that I could get? So by looking at my sample space, I can see that I have the option of heads, heads, which means I got 2 heads. I also have the option of head, tails, and tails, heads, which means that I only got 1. Then I also have the option of tails, tails, which means I got 0 heads. So my options for the number of heads when I flip a coin twice is 0, 1, and 2. Just by looking at the sample space, you can tell that those are all my options. So I could get 0 heads and I could have a tails, tails. Or I could get 1 head and I could have a heads, tails, or a tails, heads the whole time. Or I could get 2 heads and flip heads, heads. All right. So now what's left is just filling in the probabilities of each one of these situations. So to get 0 heads, let's see how many events in my sample space satisfy. So if I get 0 heads, my only option, my only option is tails, tails. Because in all the other options, I have at least 1. So I either have heads once or heads twice. So the only option for having 0 heads is getting tails, tails. So that's 1 out of 4 things in my sample space, which means that its probability is 1. And then my next option is 1 head. So let's see how many things satisfy that. So I could either get tails, heads, and that's 1, or I could get heads, tails, and that's still just 1. So I have 2 out of 4 things in my sample space that satisfy that. So its probability is 2/4, which is also just equal to 1/2. And then lastly, oh, I think I erased the top of my teeth. Or no, that's supposed to be heads, heads. There we go. So lastly, we have the option of 2 heads. So there's only 1 thing that satisfies that here. Oh. And that's heads, heads. So that's 1 out of 4 things in my sample space, which means its probability is 1/4. So hopefully a lot of that feels like review to an extent. Looking at the sample space, figuring out the probability of an event happening. It's really just a way to like organize all the possible options and then the probabilities. All right, any questions on this stuff so far? All right. Okay, let's move on to the next page. So our page 2 says that we can also graph a probability distribution. So we're going to go ahead and graph the one that we just did on the last page, which is the one for tossing 2 coins. So once again, this is probably going to look pretty familiar. It's going to represent like a bar graph or like a histogram. So it's going to look something like those. So this probably won't be too difficult to learn, which is pretty familiar. So to graph a probability distribution, you're just going to start off how we usually do and draw your X and Y axes. So on the x-axis is going to go your random variable, so your x. So the number of heads in our case is what goes along the x-axis. Okay, and then we're just going to mark all of our possible options. So our options are 0, 1, or 2. So I'm just going to mark those on the x-axis. So 0, 1, and 2. All right, and then on the y-axis goes the probability. So see if I can write this nicely. And then our probabilities that we have are 1/4, 1/2, and that's it. So I'm just going to mark the y-axis in terms of fourths. So this we'll just say is 1/4. Say this is 1/2, and I'll just put 3/4 here for fun. All right, so if we go back to our probability distribution, the probability of getting 0 heads was 1/4. So let's just draw a bar above 0 that extends to 1/4. So something like that. And then the probability of getting 1 head was 1/2. So let's do the same thing here. So we'll draw a bar around 1 that extends up to 1/2. All right, and then lastly, the probability of getting 2 heads was 1/4. So we'll do the same. Okay, and that's it. That's how you graph a probability distribution. So it's pretty similar to stuff that we've already done. Looks a lot like a bar graph or even like a histogram. So you do the number of heads or whatever the options are for your x variable on the x-axis, and then you graph the probabilities on the y-axis. Any questions on this graph? Okay, well, I'm going to pause for a second and take attendance, so give me just a minute. Okay, so now we can keep going. So next, we're just going to talk about a few requirements for a probability distribution, which are going to look very familiar to things that we've talked about before. So the 2 requirements that we have here is that the sum of the probabilities of all events in the sample space must equal 1. So this is probably very familiar. We've actually said this before just when we talked about probabilities of events. So we said if you took all the events in the sample space and added up the probabilities, you should get 1. So that's kind of familiar probably to something we've talked about. And then next, the probability of each event in the sample space must be between or equal to 0 and 1. And that's another thing that we talked about with probability. So we said the probability of an event is always going to be between 0 and 1. The probability can be 0 or 1, but it can't be any smaller than 0 or any bigger than 1. So that's just a requirement for probability in general. But we see that these requirements continue on into our discussion of probability distributions as well. So if we come up to the distribution that we did earlier about the coins, let's look at our probabilities here. So we have 1/4, 1/2, and 1/4. So this does meet the requirement that each probability is between 0 and 1, because each of these are going to be in between that interval. And then lastly, we need to make sure that when we add all of these probabilities up, that we do get an answer of 1. And if you add up 1/4, 1/2, and 1/4, you will get indeed 1. So something to think about when if you're asked to like create a probability distribution, something like we did in these two examples, make sure that when you add everything up, you get 1. Because if you don't, there's something wrong there. And make sure that each probability is between 0 and 1. It's kind of a nice requirement that can help you check your work when doing one of these. Okay. Cool. So those are 2 requirements there. So given those 2 requirements, let's do some examples. So I'll do the first example. You know, actually, I'm just gonna, we'll talk about the first one and then I'll let everyone try the second one. So I have 2 examples here, and it just wants to know if the following is a probability distribution. So we have the x values of 0, 2, 4, and 6. And then we have the following probabilities on the right-hand side. So using those 2 requirements there, why don't you think about if it's a probability distribution or not? And when you have an answer, a yes or no, send me a private chat and then we'll talk about it. So I'm just talking about for now this first one. So you don't have to give me your explanation for now. Just chat me a yes or no. Awesome. So I'm getting some answers. So I did get a lot of no's, and no is the correct answer. So does anyone want to tell me why they said no on number 1?
Because this number is greater than 1 and a negative number.
Yeah, perfect. So there is a number that is below 0, so there's a negative. And then there's also one that's above 1. So yeah, that would make it not a probability distribution. That's not even a valid probability based on what we defined probability to be a while ago. But it's funny because if you add these all up, so if you add up -1, 1.5, 0.3, and 0.2, you still get 1. So it meets that one requirement that if you add up their probabilities, you get 1, but it doesn't meet the other requirement. So good, the answer on this one is going to be a big fat no. Okay, and then why don't you guys try the second example and do the same thing. So when you come up with a conclusion, chat me your answer, and then we'll talk about it. All right, I got some answers in. Once again, this one is also going to be no. So does anyone want to tell me why they said this one was no? See? Yeah, good. Perfect. So I got 2 answers. It's more than 1, or they add up to 1.1. Great. Yeah. So if you add these all up, you do get 1.1, even though all the probabilities fall within the right range. So they all fall between 0 and 1, which is great. They don't meet that other requirement. That is all for probability distribution. So that's it for section 5.1. It probably feels like a lot that we've already talked about, which is great news. So that's it for this section. Are there any questions before I move on? Awesome. Okay, so we're actually done. So let's move on to the next one. That's pretty exciting. And then let's start on this PDF. So all we're going to do today is section 5.2 from this PDF. Because this PDF is 5.2, 5.3, and then the first section of chapter 6. So my goal is today to just do section 5.2, and then on Thursday, we will touch on 5.3 and 6.1. Hopefully finish up those two sections. That way we can move on the next week. So I'm not thinking that this is going to take the whole class period. I think we're only doing, let's see. It's about like 3 pages of notes, which is not much. So we'll probably get out early today, which is kind of exciting. So let's just get right into it. So section 5.2 is mean, variance, standard deviation, and expectation. Exciting because you should already know 3 of those words. So you should already know what mean and variance and standard deviation are. The only word that should be new is expectation, or what's called expected value. And we will get into that, and you'll actually see that it's something that you really already know. But let's go ahead and start this off. So the mean, variance, and standard deviation for a probability distribution are computed differently from the mean, variance, and standard deviation for a sample. So we talked about computing the mean, variance, standard deviation when you were given like a data set. So when you were given yeah, I can probably change the way my lecture notes look. I will address this at the end of class, but yes, I'm open to changing that. Okay, so we talked about how to compute mean, variance, and standard deviation with like a data set. So I know on the exam I gave you some like, just numbers, like I think one was what, like the percentage of high school graduates or something. So you could compute the mean by adding all of those numbers up and dividing by the total amount that you were given. So we talked about that and then doing variance and standard deviation. But this is a little different. So what if you have a probability distribution? So what if you're just given the possible outcomes and then their probabilities? So how would you compute mean, variance, standard deviation with that? Obviously, there's no like data points to just add up and then divide by the total number. And the way we discussed doing variance and standard deviation also uses the concept of like subtracting the mean from each data point. Okay, well, what if we don't have a set of data points? What if we just have this distribution? So this is where we have to discuss a different way to calculate these. And we're going to try some new approaches here in order to do this for our probability distribution. Before we do that, just recall when we talked about a parameter and a statistic, when we talked about those differences. So a parameter has to do with a numerical summary of a population. So when you're using a population, that was called a parameter, and when you were using a sample, it was called a statistic. So when you summarize a probability distribution, we're essentially working with a population. So we're going to call these parameters. So the mean, variance, standard deviation, expectation, these are considered parameters, just for reference. They're not considered statistics. Okay, so the first concept is the mean. So the mean of a probability distribution is denoted by the parameter mu. So this probably looks familiar. we defined mu before and said that it was also the mean. So this is mu again, but it's just the mean of the probability distribution. So it's actually defined to be mu is equal to the sum of x times p of x, where the sum is taken over all possible values of x. So if you have a discrete random variable and we want the mean of that distribution, we're going to take each possible value of x and multiply it by its corresponding probability, and then we're going to sum all those up, and that's going to give you the mean. But before we get into an example, like usual, we have those rounding rules that we talk about, how you should round these things. So you should round to one more decimal place than x has. So this is pretty consistent with when we did the mean before. We said when you're rounding the mean, round to one more place than the data points have. So same here, how many ever decimal places your x has, like all those values of x, do one more for the mean. Oh, same for variance and standard deviation, not just mean. I should have said that. So this holds for mean, variance, and standard deviation. So the one decimal place more rule for all three of these values. I know it probably sounds kind of picky to be like, hey, we want only one decimal place more, but this is where we've chosen to be picky, is on the decimal places. So important. Okay, let's do an example here. So let's find the mean of the following probability distribution. So this distribution gives you the number of home runs per game, and then the probabilities for each. So in order to find the mean, we're just going to follow that formula that says to do each x. So it doesn't say here, but this is x, and then this is p of x. So it says to take each x and multiply it by the corresponding probability. So let's do that. So the first x value is going to be 0. So I have 0, and then I'm going to multiply it by its probability, which is 0.23. My next value of x is 1. So I'm summing all of these things up. So I'm going to add 1 times its probability, which is 0.38. And then I'm going to add again, and I'm going to do 2 times its probability, which is 0.22. And then I'm going to add to it 3 times its probability, and then adding 4 times its probability, and then I'm going to add 5 times its probability. Okay. Obviously, I'm not going to do this by hand, so I'm going to whip out my calculator and just compute this. So 0 times 0.23 plus 1 times 0.38 plus 2 times 0.22. And feel free to follow along and try this on your own and make sure we get the same answer. Okay, so when I do this, I get an answer of 1.38. So the mean of this probability distribution is 1.38. So this kind of tells you that maybe on average, around 1.38 home runs occur per game. If you remember, I want to say this was probably week 1, maybe week 2. When we talked about means, we talked about a weighted mean or a weighted average. This is similar to that. So the concept of giving things more weight in the mean than others. So you can see the values of x that have a higher probability contribute more to the mean than others do. That's just me connecting concepts. All right, any questions on how I got 1.38? Great, cool. So let's go ahead and do an example again. So I will let you all try this one. So it says to find the mean of the probability distribution we constructed for the number of heads when you toss a coin twice. So this was on a different PDF, so I'm going to rewrite the probability distribution just so you have it. So remember we said number of heads, and this was X, and then P of X. So we got 0, 1, and 2. And this was 1/4, 1/2. Okay, so now that you have this probability distribution, go ahead and try to find the mean using that formula and the same method we used on the last one. And then, like usual, private chat me your answer when you get it, and then we'll go over it. Okay, so I got some answers in. All the ones that I have so far are correct. So I have an answer of 1. So good job, everyone. Those are all correct. So let's just go through how we got an answer of 1 just to make sure everyone's on board. So we take X and we multiply it by its probability. So this is equal to 0 times 1/4. And then we add to it 1 times 1/2. And we add to it 2 times 1/4. This is equal to 1/2 plus 2/4. And 2/4 is just a half. So this is equal to 1/2 plus 1/2, which is 1. So that means that on average, you can expect to get 1 head. So if you toss a, coin twice, you could say, okay, on average, I get about 1 head. So, okay. Any questions on finding the mean using a probability distribution? Awesome. Okay. So that is all about mean. Now we're going to get into variance. Oh my gosh, sorry. Okay. Now we're going to get into variance and standard deviation, which, at least in my opinion, I think calculating variance and standard deviation with a probability distribution is nicer than what we did before. And it's not too different than what we just did, actually. So let's talk about it, and then we'll do some examples. So the variance of a probability distribution is denoted as sigma squared. For a discrete random variable is found by multiplying the square of each outcome by its corresponding probability, summing those products, and then subtracting the square of the mean. So it's kind of similar to what we just did, but instead of just multiplying x by its probability, we're going to multiply x squared by its probability. And then we sum all those up and we subtract the mean squared. So I think this is nicer than the way that we did it when we were given a sample or some data points to use. So to me, this is a little nicer. And then the standard deviation, just sigma, is actually just the square root of the variance, which is what we talked about before. So we talked about variance and standard deviation. The standard deviation is the square root of the variance. So once you've found the variance, you've done all the heavy lifting. And the last part is just taking a square root to find the standard deviation. So the same holds here for probability distributions. Let's just get into doing an example. So this is going to use the same example with the home runs. So we're going to be calculating the standard deviation and the variance for that example with the home runs per game. Okay, so like I said, we have to take each x value and square it and multiply it by its probability. So let's do that. So I'm going to just put some brackets around here. So the first value, sorry, I'm going to scroll up. So the first one was 0 home runs and it had a probability of 0.23. So I'm going to do 0 squared times its probability of 0.23. And then for the next one, if we come back up, we had one home run and a probability of 0.38. So I'm going to come down and add to it 1 squared times its probability of 0.38. Okay, so the next one was 2 home runs. So I'm going to do 2 squared and multiply it by its probability of 0.22. Next one was 3, so I'll do 3 squared and multiply it by its probability of 0.13. And then my next one was 4, so I'll do 4 squared and multiply it by 0.03. And lastly, I had 5 home runs, so I'll do 5 squared and multiply it by its probability of 0.01. So right now, I went ahead and did this part of the equation. So I did the sum of x squared times its probability. And lastly, we just need to subtract the mean squared. So if you come back up to our example, we calculated the mean as 1.38. So I'll subtract 1.38 squared. Minus 1.38. All right, so I'm just going to use my calculator and go ahead and do all this. So 0 squared times 0.23 plus 1 squared times 0.38. Like I said, you can follow along with me, make sure you get the same thing. Plus 2 squared times 0.22 plus 3 squared times 0.13 plus 4 squared times 0.03, 5 squared times 0.01. Okay, so when you just do that portion, you should get 3.16, and then we just have to subtract 1.38 squared from it. Okay, so doing that on my calculator, I get 1.2556. And then of course, I'm going to round that to just 1 decimal place because all of my x values were whole numbers. So I'm going to give this 1 decimal place. So rounded, that gives us an answer of 1.3. So my variance is going to be 1.3. And then I still have to calculate the standard deviation, but this is not too bad once you have the variance because this is just the square root of 1.3. So using my calculator, I get about 1.14. And if I just round that off to 1 decimal place, it's just 1. Okay, awesome. Any questions on how I did standard deviation and variance here?
I have just the one. When you put it in, did you put like it into your calculators into those brackets as well, or no? Just a quick question.
I just count, so if you were gonna put the whole line in at once, so if you were gonna do the 0 squared times the probability, whatever, and then subtracting from it 1.38 squared, if you were gonna do that whole line, so let me sort of put on here. So this whole thing, I would put brackets around it. But when I put it into my calculator, I did them separately. So I didn't use brackets. But if you wanted to put that whole line in at once, you could and just put brackets around the first. I don't even know if you technically need to, but sometimes calculators are a little weird. And like sometimes they just do things in like a weird order or like I don't know. Sometimes things just happen weird when you don't put brackets in or tell your calculator what to do. So I'm not sure that you would technically need it here, but I'm always more cautious because sometimes when you don't do things like that, you'll tend to get like a wrong answer or something. But that's just me probably being cautious. I'm sure if you didn't do it, you'd be okay. I also put them in my work for the sake of distinguishing between what is x squared times p of x and what is the mean squared. So they were more for me, but the calculator would not hurt to use them. Good question. Okay, let's do another example. So we're sticking with the coin toss here. So go ahead and calculate the variance and standard deviation for the number of heads when you toss a coin twice. So in case you need a quick reminder, this is our probability distribution. So go ahead and try calculating the variance and standard deviation, and then, per usual, private chat me when you get those answers, and then we'll go over them. Okay, so I got a few answers for the variance, and I did get, I think, one answer for standard deviation. So far, it looks pretty good. So let's go over it as a whole. So far, they look pretty good. Yeah. Okay, let's do it. So same way that we did the last example, we're just doing, first we take each x value and square it and then multiply it by that probability. So 0 squared times 1/4. Next, we do 1 squared times 1/2. And then we add to it 2 squared times 1/4. And then that's the first part of the equation, and then we need to subtract the mean squared. So we found that the mean for this probability distribution in our past example was 1. So we'll subtract 1 squared. Okay, and if you just throw this in your calculator or do it in your head or do it out by hand, this is 3/2 minus 1, which is 1/2, or 0.5, which I got. I think everyone told me that was the correct answer. So nice job, everyone that sent in their answers. And then, like I said, once you have the variance, that's really the hard part. For the standard deviation, you just take the square root of this. So this is the square root of 0.5, which this gives you 0.707. But we just want one decimal place. So our answer is 0.7. Oh, actually, hold on. Is our probability, no, we're just talking about x. Never mind. Sorry, got tripped up for a second. One decimal place, so 0.7. All right. Everyone that sent those in said those answers. So are there any questions before I continue? Cool. We're actually on to our last topic for the day. It's pretty exciting. I thought we would end early. So our last topic is called expectation. And this is the one that's kind of new that we haven't discussed before, but you'll see that it's not really new. So let's just go ahead and get into it. Another concept closely related to the mean is the concept of expectation. So this is also referred to as expected value. Expected value has wide uses in the insurance industry, gambling, and other areas such as decision theory. So this is a pretty useful concept. So we'll talk a little bit about what it is, and then we'll do some examples that have to do with kind of like raffles and like gambling and stuff. So let's actually define it. The expected value of a discrete random variable of a probability distribution is the theoretical average of the variable. The way we denote expected value is E of x. So the expected value of x is denoted as E of x. So look at this below it. Does this look familiar? So anyone want to tell me what this looks like that we've already done today? So the formula for this is x times p of x, and you sum all of those up. So what did we calculate earlier that was the same?
Distribution.
Close, but the first thing we did in is that we did a standard deviation variance, but we did one thing before those. Anyone can answer, not just Michael. Anyone.
Oh, the mean.
Yeah, there we go. Thank you, Michael. It is the mean. So it looks just like the mean. It's actually the same formula. So hence the way we have mu here. So does this look familiar? Yes, it looks like the mean. mean, it also looks familiar to like standard deviation, because standard deviation and variance weren't that different from the mean. So it does look familiar to those, but it is identical to how we calculate the mean. It's really interesting because, like I said, we're not really learning anything new. We're now just introducing this thing called expected value, which is actually just the mean all over again. So let me explain, or let me do an example and then kind of explain what this means. Because it's great to know how to calculate it, but if you don't really know what expected value is or what it tells you, then it's not really useful. So let's see why it is useful when we talk about gambling or like betting or stuff like that. So this first example that we're going to do says, suppose 1,000 tickets are sold at $10 each for a used car valued at $5,000. What is the expected value of the gain if you purchase one ticket? Okay, so we're going to define our random variable x as gain. So what this means is like, what are the possible like gains if you purchase a ticket? So if you purchase one ticket, what are the possible outcomes here in terms of money you could gain? So the first thing that you could think of is if you purchase one ticket and you win, how much money have you gained? So there's really two outcomes. Either you purchase a ticket and you lose and someone else wins, or you purchase a ticket and you win. So if you win, what have you gained? Well, you've gained a used car valued at $5,000. So that's what you gained. But you spent $10 on the ticket and you're not getting that back. So I invested $10. I got a used car worth $5,000. So my gain is $5,000 minus the $10 I spent on the ticket. So if I win, I gain $4,990 because I gained a $5,000 value in the car, but I bought that ticket that was $10 and I'm not getting that $10. Okay, well, if you lose, you're not getting the car, you're just getting nothing back, actually. So if you lose, you're actually out $10. So you've lost $10. So your gain is negative $10 if you lose. So let me write down, this is if you win, and this is if you lose. Okay, so now we just have to identify a probability that goes with each of these. So my probability of winning, so gaining $4,990. Let's see, I bought one ticket and 1,000 were sold. So I have a 1 in 1,000 probability of winning. It's pretty low. My probability of losing is pretty high. So remember we discussed the complement of events. So if my probability of winning is 1 over 1,000, my probability of losing is 1 minus 1 over 1,000, which is 999 over 1,000. So I have a very high chance of losing, a very low chance of winning, but a huge gain if I do win. Okay, so our question wants to know, what's the expected value of the gain if you purchase one ticket? Okay, well, we've filled out the probability distribution. So now we just have to go ahead and calculate expected value. But when we defined it, we know that it's just the sum of x times p of x. So that's not too bad. So this is equal to, my first x is 4,990. And I'm going to multiply it by 1 over 1,000. So that's the probability that I gain that much. Okay, and then I'm going to add to it, my next possible one is a gain of negative $10. And the probability of that happening to me is 999 over 1,000. Okay, well, if I plug this into my calculator, let's see what we get. Okay, so this gives me an answer of negative $5. All right, so this might pose an interesting question of like, what does that even mean to have an expected value of -$5? Because you're probably looking at it and saying, my only two options is that I lose $10 or I gain 4,990. So how is the expected value -$5? Like that doesn't really make too much sense. So the expected value is really the average of the losses of all the ticket holders. So if you take an average losses of all 1,000 ticket holders, you'll get -5, or you'll get $5. That's like the average loss. So it's not necessarily saying, oh, you are expected to lose $5. No, because really, like, you're either going to gain that much or you're going to lose $10. But it's saying that's kind of the average losses for each of the 1,000 ticket holders if you average. Another way of looking at it, so this is another way that the book says, which I think is kind of helpful. So if you purchased a ticket each week over a long time, so you did this every week, your average loss would be about $5 a ticket. Because theoretically, on average, you should win the television set once for every 1,000 tickets you purchased. So if you do this a long time and purchase a ticket every week and participate in this raffle every single week for a long time, your average loss would be about $5 per ticket. So that's kind of the way to think about it. It's not saying you're expected to lose $5 on this one raffle, because that doesn't really make any sense. But you could think of it as the average losses among the 1,000 ticket holders, or if you did this for a very long time, you would be expected to lose about $5 for every ticket that you purchased. Okay, well, it kind of makes sense because the odds of winning are really, really slim, and the odds of losing are huge. So it makes sense that the expected value would be a loss if you think about it. Okay, let's do one more example. So this is very, very similar. It is 1,000 tickets are sold at $1 each for a smart television valued at $750. What is the expected value of the gain if you purchase one ticket? So I'm going to let you all try this one on your own. It's basically the same as the last example. You're just using different numbers in this scenario. So I'm going to let you try it, and then chat me your answers when you get it. And we will go over this one too. All right, so I got some answers in. A lot of them look pretty good. Let's go ahead and try doing it together. So similarly to the last problem, let's think about the two scenarios here. So you purchase one ticket and you either win or lose. So if you do win, you get a smart television valued at $750. So you gained that, but you bought a ticket that was worth $1 and you're not going to get your dollar back. So your total gain would be 750 minus 1, so 749. And this is if you win. And again, that's because you're not getting that dollar back that you spent on the ticket. So your total profit is 749. Our other scenario is if we lose, which means we spent $1 on the ticket and I'm not going to get that back. So that means that my gain is negative $1 because I lost $1. Okay, well, my probability of winning, I bought 1 out of 1,000 tickets. So that means my probability of winning is 1 out of 1,000. And like before, my probability of losing is 1 minus the probability of winning, which gives me 999 out of 1,000. So again, I have a very high chance of losing, but the gain is a little less on this one than our last example. Okay, so the expected value, we're going to take the first value of x, which is $749, multiply it by 1 over 1,000, the probability that I gain that much money. And then I add to it and multiply it by negative $1 times this probability 999 over 1,000, which is the probability that I lose, and I lose $1. Okay, so if I plug this into my calculator, all right, this gives me negative 0.25. Right, so my expected value is negative, well, it's to lose 25 cents. Again, this doesn't mean that you lose 25 cents, since either you can win the television or you cannot. It just means that on the average of the losses is 25 cents for each of them. Okay, and then at the bottom of this section, okay, the last thing in this section talks about gambling and expected value, which I think is kind of interesting. So if the expected value of the game is 0, then the game is said to be fair. If your expected value of a game is positive, then the game is in favor of the player, because that means on average, people are winning. So your gain is positive. So you're walking away with something. And if the expected value of the game is negative, the game is said to be in favor of the house. So in other words, the players lose money in the long run. So you can see in these two examples that we did, it's definitely not in favor of the people buying the tickets because both of the expected values are negative. One is $5 and one is 25 cents, but they're both negative. So it's definitely more in favor of the person doing the raffle, not the people playing. Lastly, shocker, every game in Las Vegas has a negative expected value. So every game is not in favor of the player. So in the long run, you will lose money. So really interesting that you can kind of see, oh, do I want to play this game or not based on the expected value. So that's going to wrap up section 5.2 for us. All we're going to do on Thursday is do the next two sections. So 5.3 and then 6.1. And we're going to get into some types of probability distributions. And we're going to discuss those and like the properties that they have. So let me stop my recording really quick.